Hello everyone, welcome back to the channel uLearn Education Online.
Today we are going to discuss the practical differentiator design using op-amp. This is the continuation concept of ideal differentiator circuit using op-amp. So in the previous video we have discussed in the ideal differentiator concept, that is how to derive the output voltage expression and how the IO waveform shape look like and how to obtain the frequency response plot. Okay, so in brief, if you discuss the frequency response plot of ideal differentiator op amp, so this is the circuit of ideal differentiator op amp that is used, and the frequency response plot for this kind of circuit is this is the one. If you observe here, FA indicates the cutoff frequency of this differentiator circuit. Here the gain in dB is increasing at high frequencies, which means that this circuit output voltage will goes to saturation when it is operated with the high frequency input signal, which makes this ideal differentiator circuit to enter into unstable. If you say that the system is unstable, the system will going to oscillate. So at high frequencies this output voltage will goes into the saturation and this system will be in unstable, and this is the major drawback if you use this ideal differentiator circuit at high frequencies. And the second drawback is, if you observe here, the input signal is directly connected to the capacitor. If you observe the capacitive reactance, now what is the capacitive reactance? We know that XC is 1 by omega C. Here the omega we can write in terms of frequency as 1 by 2FC. So the reactance of this capacitor is 1 by 2 pi Fc. Okay, so at high frequencies this capacitance value will be equal to 0, means if f is infinite, ideal case, this C1 value will be almost negligible, which makes the circuit will allows the noise component and also it greatly amplifies the noise signals. So these are the two major drawbacks of using ideal differentiator circuit at high frequencies. So in order to overcome these drawbacks, we have to externally use some passive elements in such a way that it has to overcome the two drawbacks. The first drawback is, at higher frequencies the gain must be increased because of using ideal differentiator. If you add a component in such a way that at higher frequencies if the gain tends to decrease, then that drawback will overcome and the system will be stable. Okay, so this is the idea of using practical differentiator in order to overcome the drawback of ideal differentiator circuit. Now we are going to see what is a practical differentiator circuit and how to derive the output voltage expression of practical differentiator circuit and how the frequency response of practical differentiator circuit looks like. So this is the circuit that is used to design a practical differentiator circuit from the ideal differentiator in order to overcome the drawbacks that is faced by using ideal differentiator circuit. So if you clearly observe this circuit, to the ideal differentiator circuit some external elements are added. Now what are the external elements? That is R1 and CF. Now why these two values are added means, if you observe for in the ideal differentiator circuit, as the frequency is increasing, the gain of the circuit will goes on increasing. So we have to decrease the gain at a higher frequencies in order to indicate the particular frequency at which the gain should be decreased. For that purpose we are using resistances and capacitances that is externally added to this op amp circuit. Okay, that is the major use of using the resistance and capacitance, and why it is used in feedback and why it is used in series with resistance we are going to see at the last of the video. Okay, now just see how to obtain the output equation V naught in terms of the input equation. Now here if you observe the circuit, the current equation we can apply the KCL at a node B. That is, the algebraic sum of entering currents will be equal to the algebraic sum of leaving current. So we can write I is equal to I1 plus I2. Now we have to know what is the node voltage at B, or a node voltage at the inverting terminal. Simply we can see that the node voltage at A will be equal to the node voltage at B. Here we know from the basic rule of op-amp, that is, the entering currents at the inverting terminal and the non-inverting terminal of op-amp is 0. So here the entering current at the node terminal is A is 0, which means that 0 current will flow through the OR compensation resistor. So indirectly the node voltage at the non-inverting terminal of op-amp is 0. Since VA is 0, VB value will be equal to 0. Now simply apply the KCL rule, that is I is equal to I1 plus I2, and from the using a Ohm's law we can write the current equation as I as VI minus 0 by the total impedance, nothing but R1 plus 1 by S into C1. And here the I1 expression is 0 minus V naught of S by RF, and I2 expression is 0 minus V naught of S by 1 by S into CF. Now if you take the common V naught of S expression, then it is 1 by RF plus S into CF, which is equal to, take the LCM for this expression, that is minus VI of S into SC1 by 1 plus R1 into SC1. Now finally, if you simplify this equation, we will obtain the transfer function for this op-amp circuit is minus S into C1 RF by 1 plus S into R1 C1 1 plus S into RF CF. Now come to second drawback of ideal differentiator circuit. So in the second drawback of ideal differentiator circuit, for the higher frequencies the capacitive reactance is negligible, means it allows the noise components. Now we have to maintain a relation in such a way that this op-amp circuit will reject the noise components. In order to maintain that, we have to maintain this product of R1 C1 should always be equal to the product of RF CF. In that case only we can say that this output voltage will reject the noise signals at the input. Okay, so if you maintain this relation, then we can write V naught of S by VA of S is equal to minus S into C1 RF by 1 plus S into R1 C1 whole square. Now this is the equation 1 for this practical differentiator circuit. Now we have to prove that this obtained equation is nothing but a differentiator equation. Differentiator in the sense the output voltage obtained is the differentiation of input. In order to prove that condition, we are assuming that the product of RF C1 should always be greater than the product of R1 C1. Okay, this case is assumed in order to prove that this circuit will act as a differentiator circuit. So if you assume this expression, then from this we can say that this denominator term will be negligible, and finally the equation obtained is V naught of S is equal to minus S into RF C1 into VI of S. If you take the inverse Laplace transform to this expression, then the S domain equation can be converted into time domain equation as V naught of t is equal to minus RF C1 into d by dt of VI of t. Here this RF C1 is nothing but a time interval or a pulse width, and here the input signal is the differentiation of uptime. Okay, so the output signal we can simply say that it is nothing but a differentiation of input signal. So this circuit will act as a differentiate. This is how we have proved this practical circuit will also act as a differentiator, and how it overcome the drawbacks of ideal differentiator circuit. Now here the next is we have to observe how the waveforms of the practical differentiator looks like. The waveforms of input signal and output signal of this practical differentiator is same as the waveforms that are discussed in ideal differentiator circuit. So directly we are going to see how the frequency response of this practical differentiator circuit looks like. Okay. So now we are going to see the frequency response. So in the frequency response, we have to obtain the relation between the gain and the frequency of the circuit. So in order to obtain the relation between gain and frequency, we are considering the derivation what we did in the previous slide, that is we are finding the transfer function v naught of s by va of s for the practical differentiator circuit. Already we have find, which is minus s into c1 rf by 1 plus s into r1 c1 whole square. Okay, so in order to obtain or convert the S domain to F domain, simply we use the relation, that is S is equal to j omega. Here replace omega as 2 pi f. Finally the equation we are obtaining is v naught of j omega by vi of j omega is minus j 2 pi f rf c1 by 1 plus j 2 pi f r1 c1 whole square. From this equation we are obtaining the cutoff frequency and some unknown frequency fb. Here the cutoff frequency we are assuming is 1 by 2 pi RFC1. So this is the cutoff frequency that is same we are assuming in ideal differentiator circuit. Now we have to see what is this term, that is 1 by 2 pi R1C1. This is the denominator that is present. Okay, so this frequency FB is nothing but the indication to the circuit at which the gain has to be decreased. Okay, so here FA is the cutoff frequency and FB is the indication for the circuit to the gain should be decreased. So if you substitute this equation, we can obtain the v naught of j omega by vi of j omega is minus j times of f by fa by 1 plus j into f by fb whole square. So this is the final equation we have obtained. From this we have to find out what is the magnitude of the transfer function, magnitude of a gain, and how the frequency response looks like. So we can find out the magnitude A as, simply take the modulus of your transfer function. By using a complex equation we are obtaining the magnitude A as f by fa by 1 plus f by fb whole square. If you write the gain in dB, nothing but 20 log A to the base 10. So we can find the gain in terms of dB, and also we know that we have to find out which frequency value will be high, whether this cutoff frequency value will be high or the fb value, that is unknown frequency value, will be high. We know that this relation should be maintained. Fa should always be less than fb. Why the fa should be less? Since fa is a cutoff frequency and fb is the indication at which the gain should be decreased. Simply in words we can say that this fb is the highest frequency compared to the cutoff frequency, which is lowest. This is one assumption from the theoretical. Or if you maintain the relation, that is rfc1 is always greater than r1c1, from this equation we can write, since this rfc1 is always higher, this fa value should be less compared to the fb value. Okay, if you observe this plot, below the fb value the gain is increasing, and once it reaches to fb frequency, then the gain starts to decrease. So we can say that from this relation, by using this practical differentiator circuit or by adding external elements, that is R1 and CF, to this circuit, the gain is limited, means the system will be unstable, and also we have maintained the relation, that is R1C1, which is always equal to RFCF. Okay, so since we are maintaining that relation, the noise components are greatly rejected by the circuit. This is how the practical differentiator circuit uh, user, and how and the disadvantage of using a practical differentiator circuit with the see, ideal differentiator circuit. In the next we are going to see how to design this practical differentiator circuit, what are the necessary assumptions has to be made.